Hi, ladies and gentlemen. Ladies and gentlemen, this lecture will be the completion of section 11.2. It's going to be a short lecture because I was up grading yesterday evening all evening. So I'm going to get started, but I'm going to start with a little bit of some remarks on logic, mathematical logic. So shall we begin? So logic begins with propositions, which are just the same thing as assertions, which may be true or false. Usually they're denoted in uppercase letters like P. P might be the proposition. The sky is overcast, for example. That may be true or false. Today it's false, for example, at least from where I'm sitting. And then you could have another one, Q, the sun is not visible. Of course, these are not equivalent statements, right? Because, for example, it might be nighttime, so the sun is not visible for a different reason, even though the sky may be clear. There are also negation, the notion of negation. You can take an assertion, a proposition, and negate it. So, for example, and usually is denoted by this symbol here, this squiggle, so not P, which means the negation of the sky being overcast, which means that the sky is not overcast. Not Q would be the sun is visible, because that's the negation of the sun being not visible. Okay, so there's the notion of implication in logic, which is a statement of the form, you would write it with a one-way double arrow, and this means P implies Q. This is a new proposition, which may or may not be true. So this would be the statement in this case, if the sky is overcast, then the sun is not visible. Now, we have other ways of forming implications, which may or may not be equivalent to this proposition. So by the way, two propositions might be equivalent, which means that one implies the other. If P implies Q is true and Q implies P, we write P if and only if Q. P if and only if Q, and this is called a tautology. Okay, so we have that. Okay, so now we also consider something called the contrapositive. The contrapositive is the statement of P implies Q is the statement that not Q implies not P. So not Q implies not P. So how would we read that in English? In English, we would read that as the statement, if the sun is visible, then the sky is not overcast. Let me make some more space for the word overcast. Okay, so that's not Q implies not P. Now, P implies Q was the statement that if the sky is overcast, then the sun is not visible. Overcast implies the non-visibility of the sun. So therefore, but that's that's obviously, or if you think about it, that's tautologous to or equivalent to, if you don't see the sun, I'm sorry, if the sky is, okay, so I have to start over. Overcast implies the sun is not visible. The contrapositive of that is if the sun is visible, the sky isn't overcast. If the first sentence is true, if the sky is overcast, then the sun is not visible, then this last sentence is also true. If the sun is visible, then the sky is not overcast. So what I'm trying to say, and I will clear it for you. I'll make it the statement, and this isn't always a true statement. It's a tautology that P implies Q is always equivalent to not Q implies not P. So a statement or an assertion is always equivalent to its contrapositive. Okay, so for example, if it's true that I always eat when I'm hungry, if that's a true statement, that if I am hungry, then I always eat. If I am hungry, then I eat. If that's a true statement, then the contrapositive would be if I don't eat, then I am not hungry. In other words, if this implication always holds, every time I'm hungry, I eat, then if there's a time when I don't eat, that would mean I'm not hungry. Great, okay. So I want to make one more mention of something which is not in a this was a tautology, this statement. A statement is always equivalent to its contrapositive. There's something also called the converse. That would be the assertion not Q implies not P. So in the above, not Q. Oh, that's not true. I take that back. That's the contrapositive again. The converse is the statement Q implies P. Now Q implies P is not equivalent to P implies Q. It's not a tautology. For example, what would it be in the case of hungry and eating? Well, if Q is the statement I eat and P is the statement I'm hungry, then if I eat, this would be if I eat, then I'm hungry. That is not equivalent to the statement if I am hungry, then I eat. Because you can imagine eating even when you're not hungry, right? That would be the reason. So don't confuse the converse from the contrapositive. There was a reason I did this just now, because a lot of these tests we're going to be introducing for series require you to understand logic, a little bit of logic. So this is the logic, all the logic we need, I believe, for that. Okay, so we're done with the logic. I want to get on with the real lecture today. Okay, so let's let summation A sub n be a series, an infinite series. Okay, so here is a fact. that, or you can call it an assertion or a proposition, if sigma a sub n is convergent, then the limit as n goes to infinity of a sub n must always be 0. Okay, that is the nth term, the sequence associated with the series, the nth term of the series, that limit as n goes to infinity must be 0. And here's the proof of the fact. So let's let Sn be the nth partial sum. So that would be the sum over ak. K goes from 1 to n. Then then a sub n is equal to Sn plus 1 minus S sub n. You add up the first n plus first 1 terms of the series, and then you subtract off the first n terms of the series, the sum of those n terms, and you'll get a sub n. You're just getting one extra term when you look at Sn plus 1. Okay, so then the limit as n goes to infinity of a sub n is the limit as Sn plus 1 minus S sub n as n goes to infinity. But that's the same as we can break up the limits, assuming each term converges, and it does by assumption, because we're assuming this is convergent. Now the limit of S sub n is the limit of the series. We can call that S, but that's the same as the limit of Sn plus 1. So you get S minus S, which is 0. And that's it. That's all you have to do. We've proved it. Okay. So what does this all mean for us? Well, I want to say the contrapositive of this. Let me go back. So if a sub n is convergent, then the limit of a sub n is, if the series is convergent, then the limit of the terms of the series a sub n is 0. The contrapositive would be to negate that. If the limit is not 0, then the series is not convergent. In other words, the series is divergent. So that's the statement I want to make. So this is called the divergence test. It goes like this: if the limit of a sub n for a series a sub n is not 0, then, and the implication is in this direction, the series summation a sub n is convergent. Okay, so notice this note, and this is very important. The converse fails. Okay, so we'll see why. Okay, so for example, we know that let's consider the series summation 1 over n. Okay, so the limit of a sub n is the limit of 1 over n as n goes to infinity, which is 0. But the series diverges anyway. So this test does not help us here, right? Because even though the limit is 0, it doesn't say anything about the series, the test. But here's a place where it will help us, the test, summation n over n plus 1 as n goes from 1 to infinity. The limit of the nth term of the series is n over n plus 1, and that's going to be 1. So this is going to diverge for that reason by the test. So the test cannot always be applied. That's what I'm trying to say. This series diverges. Okay. All right. So here are some properties of convergent series that are useful to consider. So suppose summation a sub n and summation b sub n converge. Then summation a sub n plus b sub n converges and is equal to the summation of a sub n plus the summation of b sub n. So the sum of the series converges. Okay, and the second important property is that if I take a series and multiply it by a constant, each term by the same constant, then they can move the constant through, it'll still converge. But this is telling you what it converges to. Okay. So for the remainder of today, I want to just consider some examples. And this, I said, was a short lecture. So here's an example. The sum n goes from 1 to infinity of 1 plus 1 plus e to the minus n. Okay, so what is happening to the nth term? Let's see if we can apply the divergence test to this. So what is 1 over 1 plus e to the minus n? Well, as n is going to infinity, notice that this is 1 plus 1 over e to the n. We can rewrite it that way. This n, as n goes to infinity, this term goes to 0. So this tends to 1. So a sub n does not tend to 0. So by the divergence test, the series diverges. Okay, here's an example. How about the sum? N goes from 1 to infinity of 2 to the n plus 4 to the n over e to the n. Well, if we can break it up as a sum of two convergent series, we can say what the answer is. So this would be, assuming there's convergence, 2 to the n over e to the n plus the sum 4 to the n over e to the n. And n is going from 1 to infinity in both cases. And this is, it's probably better to write this as 2 over e and 4 over e. So 2 over e to the n, 4 over e to the n. Now, these are both geometric series with common, the first case, the common ratio is 2 over e, and the initial term is 2 over e. So this will converge to 2 over e over 1 minus 2 over e. And similarly, the second term converges to 4 over e. Oops, this is not going to work because 4 over e has common ratio bigger than 1. So this one will diverge. So how do we deal with this? Well, here's how you deal with this. Let me go back a little bit. We know the first one, 2 over e, is a number less than 1. But the second common ratio is bigger than 1. So here's what I want to suggest. We argue this way. So let me erase the a little bit of the screen here, and let's consider this again. We're going to think differently now. Okay, here's what we're going to do. Let's argue in the following way. If this thing here converges, then since the first thing on the right converges, then we would get the sum n goes from 1 to infinity of 2 to the n plus 4 to the n over e to the n minus, I'm subtracting this series from this series, 2 over e to the n would also converges. But look what happens when we do that subtraction. This is equal to the sum of 4 over e to the n, and we know that this diverges. It doesn't converge. This diverges. So what does that tell us? That tells us that our reasoning was wrong. This does not converge. This has to diverge, because if it converged, we would lead to a contradiction, because the contradiction is that it both converges and diverges. So the answer to this problem is that it diverges. Okay, so we use the fact that if we subtract a convergent series from another convergent series, what you get has to be convergent. But here's on the right side, we have a, this convergent series, which we can subtract from this series. Now, if this series converged, we'd be subtracting one convergent series from another one, and the result would have to converge. But we know that the result does not converge it diverges for a different reason. Therefore, the original series could not converge. This is called argument by contradiction. Okay, so let's try one more example, which is sort of non-standard. The sum n goes from 1 to infinity of ln over n plus 1. Now, the divergence test does not work here because n over n plus 1, that tends to 1, so ln of it will tend to ln of 1, which is 0. So the nth term, a sub n, tends to 0, so the divergence test won't help you here. What will help you here is to consider the nth partial sum. So that would be the sum nk goes from 1 to n of ln of k over k plus 1. And let's write out what that is. That's ln of 1 over 2 plus ln of 2 over 3 plus dot, 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 plus ln of n over n plus 1. Now, ln of sum of ln's is ln of the product. So this would be ln of 1 over 2 times 2 over 3 times 3 over 4, all the way up to dot, 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 n over n plus 1. Notice all these terms cancel except the first one and the numerator on the left-hand side, leftmost term, and the denominator of the rightmost term. So this would be ln of 1 over n plus 1 left over. So what happens as n goes to infinity, Sn tends to ln of 1 over n plus 1, and that is tending to ln of a very small number. And what happens to a very small number? Ln is blowing up in a negative direction. So, so the point is that this is going to minus infinity. So let me indicate that here. It's tending to minus infinity. So it diverges. So this series diverges. And I think that's enough for today. We will return next time. We'll start section 11.3. Great.